In this module, we're going to talk about what are called cell potentials. Now, when you have a galvanic cell, you have the one side of it in one cell, the oxidizing agent is pulling electrons away from the reducing agent through a wire. Now, how strongly the oxidizing agent pulls those electrons is called the cell potential, or the electromotive force, EMF, of the cell. The unit of this EMF or cell potential is the volt. 1 volt is defined as how much energy in joules per amount of charge that's transferred in coulombs is done. Now, so a volt is a joule per coulomb. Now we have ways of measuring the cell potential for an entire cell. Each half would be called a half cell. Now we can put a digital multimeter up here and measure it. There are other ways like a potentiometer and stuff like that, but mostly we use digital voltmeters. And those are nice because they can measure the cell potential pretty much directly. Now, we can measure the potential of an entire cell, but it's impossible to measure the potential of a half cell by itself. So what we do is we set a standard. We set sort of an arbitrary 0, and we set 0 as being the potential of the standard hydrogen electrode. That means that I'll show you a picture in a second, but hydrogen gas is at 1 atmosphere, and the concentration of hydrogen ion in the cell is 1 molar. That's what standard conditions mean for this. And here's a picture of it. So we have hydrogen gas coming in, a platinum electrode, and hydrogen ions. There's an acid in here. And the potential of this cell, the electromotive force, is defined as being 0. So if we hook this cell, this is the hydrogen half cell, make it a half cell is in this cell over here. On the other side, let's say we have zinc metal, zinc sulfate in solution, 1 molar. And we hook this digital voltmeter up. It ends up that the electrons will flow from the zinc onto the hydrogen. So the hydrogen's being reduced, the zinc's being oxidized, and we get a plus 0.76 volts. Now, when the electromotive force, or the cell potential for an entire cell, it's just the sum of the cell potentials for the 2 half cells. So the cell potential for this setup here is going to be the potential for the hydrogen half cell plus the potential for the zinc half cell. Now we define this one here as being 0. This we can measure, which means we now know the cell potential for zinc being oxidized is plus 0.76 volts, because this is defined as 0. You see how that works? And now what we can do, now that we know what zinc's cell potential is for being oxidized, we can hook zinc up to something else. Let's say copper metal with copper 2 sulfate in solution. We hook the digital multimeter up to this cell, and we get a 1.10 volts. Same thing, the cell potential is equal to the potentials of the 2 half cells. Now, this is the zinc is being oxidized, copper is being reduced. We know the cell potential overall because we measured it. We know what zinc's is, 0.76 for being oxidized. That must mean that if we solve this equation for the potential for copper being reduced, it has to be 0.34 volts, so that it adds up to be 1.10. And we can keep on doing this. Now that we've set our standard, we can, once we know the cell potential for a half cell, if we don't know another half cell, we can just hook it up, measure it with a digital voltmeter, and figure it out real quickly, real easily. Now, we have tables and tables of what are called standard reduction potentials. Now, here's the thing. These are all written as reductions. Remember our zinc? Zinc we wrote as being oxidized was 0.76 volts. Well, when you reverse a half reaction, you change the sign of the cell potential, the electromotive force. So because all these are written as reductions, we reversed the zinc being oxidized and made it reduced, and now it's negative 0.76 volts. These numbers over here are a measure, really, of how strongly that species can pull the electrons away from something else. So if you have, these are all half cells. Every single one of these is a half cell, and there's a lot more than this, but these are just a few. So if you have 2 of these half cells, any 2 of these half cells, when you put them together, what's going to happen is the one with the higher standard reduction potential, the more positive standard reduction potential, that's going to have a stronger pull on the electron. So it'll pull the electrons away, and it'll be reduced. And that means whatever the other one is going to be oxidized. So it's going to flip around here and going to change the sign of its cell potential. So watch. What we can do, what we do a lot with these half reactions is we combine them, and we can, if we know the two half reactions involved in a cell, we can manipulate them and add them up and get the balanced overall equation for the complete cell. In addition, we also get the cell potential. So here's what you do, real easy. You just look at the two half reactions involved, find the one that has the lowest, that is the least positive cell potential. Okay, switch it, reverse it, change the sign. So it's going to be written out. That's going to be the oxidation half reaction. Then you're going to have a certain number of electrons in each of those half reactions. Find the least common multiple and multiply each by an integer so that you get the least common multiple of that number of electrons. The electrons are going to cancel out. Next, you add the two half reactions, making sure the electrons cancel. When you add the reactions, you add the potentials. So, when you multiply a half reaction through by an integer, you do not, I repeat, you do not multiply the cell potential. Just leave it as it is. So let's say we have this cell, this electromotive cell, galvanic cell, excuse me, and we want to write the balanced equation and find the cell potential for this reaction. Now, so what I'm showing you here is, I'm giving you these two half reactions. They came from a table. Now, what you could do, this isn't balanced. You could do like we did with balancing redox reactions. You can find the oxidation states, find what's being oxidized. For instance, manganese here is +7, over here it's +2, so manganese is being reduced. And chlorine and chlorate is going to be +5, and perchlorate will be +7, so it's being oxidized. But that's not really what we're doing here. We already have these because we looked them up. Find the two half reactions, then you look at the two half cell potentials, whichever is least positive, in this case this one down here, you're going to flip it, change the sign, and then multiply through so you get the same number of electrons in each half reaction. So we kept the permanganate as it is because that was the most positive cell potential, but we're going to the least common multiple, by the way, of 5 and 2 is 10, so we multiply this through by 2, we get this right here. Okay. Now for this one, we flip it around because it had the least positive cell potential, and we get this right here in white. Multiply through by 5, and again, notice when we multiply these equations, we are not multiplying the cell potentials. Anyway, so we get this guy right here. When we add up, the 10 electrons cancel, of course. 10 of these hydrogens cancel 10 of these, leaving 6 hydrogens on the left. 5 of these waters cancel 5 of these, leaving 3 waters. When we add them up, we get this. And because we flipped this, we've changed the sign of the potential. We got a negative 1.19. And we add 1.51 plus negative 1.19, we get 0.32 volts for the overall cell potential.